When elements stretch or skew too much, your solution breaks down. In this video, we will see how omega h helps fix that. Let's do a quick analysis of mesh metrics in omega h. A mesh matrix is a mathematical description of the desired size and shape of mesh elements across the domain. First, I apply a constant metric, which means we are telling omega h that all elements should be the same size and isotropic. I run the code and visualize the mesh in ParaView. Everything looks uniform, just as expected. Now I compute the implied isotropic metric, which tells us how far the current mesh is from ideal. In the visualization, smaller elements show higher metric values. This means the mesh wants to coarsen in those regions. This is a great tool to analyze which parts need refinement and coarsening based on shape and size. So, in short, the mesh metric gives a way to define that the ideal element should be, and guides remeshing accordingly. Finally, I apply a metric based on element angles. Here I'm writing a custom metric based on element angles. It is not in the standard omega h format. Instead, for each node, I will loop through its connected elements and assign a value. 0.5 if the element has an angle beyond a certain threshold, and 1 otherwise. This is just a simple flag, so you can visually identify which elements pass the angle check and which don't. The results will be saved in a file called out.amr angle 3D, and you can easily open that in ParaView. Their blue-colored tetrahedra will indicate elements that are outside the desired angle threshold. Keep in mind, this doesn't mean those elements will be remeshed. It's just for visualization and debugging. I tag elements with very large or small angles and assign a target size, 40% of their current edge length. The rest of the mesh keeps the same size. This helps fix poorly shaped elements without remeshing the whole domain. After running omega h remeshing, the result is a more regular mesh with better element quality. ParaView shows smoother transitions and fewer distorted elements, exactly what we aimed for. Now we are visualizing the Jacobian determinant in ParaView. On the left, we see the original mesh, and on the right, the new mesh after refinement. While the Jacobian alone doesn't fully capture element quality, since it could be small without the element being distorted, it still gives us a good sense of element size distribution. Here, we can observe a more uniform pattern in the new mesh, with Jacobians being more consistent across elements. Finally, we're also displaying the plastic strain to see how it evolves through the domain. If you're working with mesh adaptation, two powerful tools are omega h and MMG, but they serve different purposes. Omega h is designed for high performance in-memory mesh adaptation. It supports parallel refinement and coarsening, works with scalar or tensor metrics, and preserves mesh topology when possible, making it perfect for incremental adaptive remeshing during simulations like Ale or Contact. On the other hand, MMG performs full remeshed based on a user-defined metric, usually through input and output files. It is robust, especially for complex geometries and controlling edge length or curvature, but it is not designed for incremental updates in memory. So if you want tight integration with your solver and GPU support, go with omega h. If you need full control over element shapes and sizing, go with MMG. In a high-strain solver, you can combine omega h and MMG all in memory to maintain mesh quality efficient. Use omega h for fast, localized adaptation, monitor strain gradients or element quality like minimum diedral angle or Jacobian. If local distortion exceeds a threshold, trigger omega h adapt with a custom metric, maybe based on angle, strain, or size function. But if degradation becomes global, unrecoverable, say a large fraction of elements fall below quality, switch to MMG. Once done, remap solution fields and continue. Other metrics and what's next. There are many other metrics we can use to assess element quality, like aspect ratio, skewness, and more comprehensive element quality measures. Omega H actually includes built-in functions to compute and even map some of these fields, so you don't need to do everything manually. If you're interested in diving deeper into mesh quality metrics, field mapping, and how to remesh using tools like the MMG library, make sure to stay tuned for the next video. If you're into FEM, SPH, CFD, remeshing, or just enjoy watching solids get squished by clever math, you're in the right place. I dive into open source solvers, CPU acceleration, and how these methods actually work under the hood. So hit subscribe, or better, hop on the mailing list at opensourcemag.com. No spam, just good stuff. And if you want to support or ask deeper questions, there's always my Patreon. Thanks for watching and happy coding!